to Agnes. And tomorrow morning, pre-talk starts at 9. For everyone else, 9:30. Pre-talk is for graduate students. And there will be a banquet tomorrow evening. And it's a pleasure to introduce our first speaker, Sun, who will be speaking on algebraic geometry of Taylor limits. Limits of Taylor limits.
Okay. Well, thank you very much for the invitation. So, I hold my problem. Taylor manifold. So, the purpose of this talk is to introduce the subject of Taylor geometry, where the algebraic geometry can be applied, and to study the relation with Riemannian geometry, and also there are some algebraic geometry questions that are generated from this study. So let's start with the classical Kodaira embedding theorem. This is the classical relation between different geometry of algebraic geometry of complex manifolds. So if X is a complex manifold. So if X admits a Taylor metric omega, which is integral, in the sense that it's in the first chain class of some harmonic line bundle L, then so X embeds into some projective space as a projective submanifold. Projective variety. So it's defined, so by Chow theorem, it's defined by a set of polynomial equations. And the converse is also true. But the proof of this theorem, so we started with arbitrary abstract complex manifold. So with this Taylor metric, we can obtain an embedding, and so the key point is to define this map, and this map is defined by holomorphic functions, or more precisely holomorphic sections of some power of L. So this theorem tells us that to understand the Taylor manifold, we can use algebraic geometry, and also we can use Riemannian geometry later. So the question is, if we have a sequence of Taylor manifolds, xi, omega I, li, so how can we take limits? So this so I'm a differential geometer. So this is formulated in the differential geometric flavor. And in algebraic geometry, this is related to the compactifying moduli space. So how can this Taylor manifolds degenerate? So we know that we cannot always stay in the smooth category. We have to allow some singular objects. And the question is, how do we make a meaningful sense of a limit? So in algebra geometry, we know that so we view this manifold as a projective subvarieties of Pn. Suppose we can embed them uniform into some fixed Pn. Then we just so each xi is defined by polynomial equations. So you just take limits of these coefficients of the polynomials. So we can obtain some limits. So if you use precise language, we need to use this notion of Hilbert scheme, which parameterizes certain classes of algebraic subvarieties of Pn with some fixed numerical constants. But if you look at this, you take a limits of defining equations. But there's a problem here. So this defining equation is not unique if you fix x, because you have a project transformation of Pn, which moves x by inside Pn, and the defining equation will change. So there's an action of this PGL n plus 1 C action. So we cannot fix for each xi, we cannot fix a unique set of defining equations. We have to allow all these actions. But then we will see immediately we have problems because this group is non-compact. Really. So limits will in general not be unique. So we just consider the example. You can embed P1, P2 as a between two curves. So this is a defining equation, but then you just use diagonal transformations of P2. This is equivalent to xy plus t is square equals 0. So these two, for any t non-zero, these two equations define the same isomorphic complex manifold. But if you let t go to 0, then this you get xy equals 0. This is a union of two lines, and when t goes to infinity, this is square equals 0. It's a double line. So even for fixed complex manifold, you can take limits, and the limit is not unique. And to get run of this problem, so there's a notion of stability in algebraic geometry. So we have to choose the good orbits in the Hilbert scheme, and then we can get a meaningful compactification of the modular space, so we can take limits. So this is the algebraic geometric point of view. But the limit, there's another issue with this limit is that if we choose a different n, try to embed this xi's into pn's, then can we get the same limit, right? So this is not a. You have to fix some ambient space in order to get a compactification. So I will not dive into this details of this, because I think everybody knows better than I do. So I would like to introduce another aspect where we can take limits. But a priori, it's quite different from this aspect. But in the end, there are relations. So we view xi, omega I, metric spaces. So it's a Kähler metric, so it defines a natural metric on xi. So just like a Hilbert scheme, we have to enlarge the objects to include singular varieties. Here we want to take limits of these objects in the category of metric spaces. So under two natural conditions, the geometric condition that the diameter, assume the diameter of xi omega I is bounded by some fixed number d. So we want to take a limit which is still compact. So if the diameter goes to infinity, then the limit won't be compact. And the second, we want to, so this is a notion that allows us to take limits. So any epsilon positive, there exists any epsilon number such that any I can find epsilon net of xi omega I with at most epsilon points. So this is our space. So we can uniformly. So an epsilon net is a subset of xi, where each point, every point of xi is within distant epsilon to this subset. So this says that for any epsilon we can uniformly approximate our xi by a discrete set of points with a fixed number of with a fixed number to allows us that we can uniformly approximate xi by discrete spaces. So this is like physics. You quantize the space, discretize your space, and then if you fix the epsilon, because you only find a number of points, and you can take limits of this discrete metric space. It's just and the limit is still discrete with this many points. And then we can take epsilon goes to 0, take diagonal limit. So get obtain x infinity, the compact metric space. So here and after, so when we say we can take limit, we always mean by passing to a subsequence. So because we need to take a subsequence many times, so we just ignore this. And this limit is called Gromov-Hausdorff limit. In other words, we have a Gromov-Hausdorff limit. This notion of limit of metric spaces was introduced by Gromov. So more abstractly, so given this sequence under this condition, we don't need the metric to be Kähler, just can be arbitrary Riemannian manifold. So Gromov-Hausdorff limit is this x infinity, but abstractly we can also find there's a metric on the disjoint unit of all this xi, x infinity. So this xi is x infinity. There's a metric on the disjoint unit such that the distance between xi and x infinity goes to 0 as I go to infinity. So distance between these two compact sets in this space, in this metric space. So a priori, this x infinity is only a metric space. So we will see later that it can make sense of algebraic structures on x infinity and certain geometric assumptions. So if we examine these two conditions, the first condition is that to ensure that the limit is compact. If the diameter goes to infinity, then the limit is not going to be compact. But this condition can be relaxed. It's not really linear. So this is a notion of a point in the Gromov-Hausdorff limit. When the diameter is not bounded, so we can fix a scale. So for this, we need to choose an extra base point, pi. Without the diameter condition, suppose the 2 is still satisfied within a fixed scale around pi. If we fix the radius r around pi, suppose 2 is satisfied, then we can take limits of this ball, the radius r ball around pi. this diameter bounded. And then we can let r go to infinity. So this converges to some limit. And then r go to infinity, you get the limit with a distinguished point of this limit of pi. Base point infinity. You think of this, if you expand a circle, and if you stand a fixed point on the circle, then the limit will be a line. You choose a base point, line. So without condition 1, then the limit is in general more compact. But we can still make sense of the limiting procedure. And the condition 2 can be replaced by a geometric assumptions related to Ricci curvature. Let's just recall if xg is a Riemannian manifold. If you take a point x in x p, then there is a distinguished coordinate chart around the neighborhood of p. It's called normal coordinate, and which the Riemannian metric tensor can be written as so you can take the Taylor expansion of so this is x, this is the coordinate chart 0 and p. So Riemannian curvature tensor, the Riemannian metric tensor has Taylor expansion, which with the vanishing first order term, and the second order term is includes the curvature of this Riemannian metric. And the Ricci curvature enters if you consider the volume form of this Riemannian metric. It also has an expansion T0, the standard Euclidean metric, and then get 1 minus 1 over 3 ij rij p xi xj. So if we expand the volume form of a Riemannian metric and in the normal coordinate chart, then the second order term gives us a symmetric tensor P, and this is so the Ricci curvature tensor is the tensor defined by this Rij. So this is a symmetric tensor, it's the same type as a metric tensor. So from this expansion, we see that the sign of this matrix controls the growth of the volume. So if this matrix is positive definite, then this volume form is smaller than the Euclidean volume form in the neighborhood of P. If this is negative, then it's bigger. So if so there's a Bishop Gromov volume comparison, which tells us not just locally at this point, but uniformly in a global scale that if the Ricci curvature of x, for example, let's say if it's bigger or equal than 0, then the volume of a ball of radius r around any point P is smaller than the volume of a ball of radius r and P in a Euclidean space. Let's say it's when you compare the ball, the volume of the ball in X with a ball in a Euclidean space, then this is always controlled. And if it is bounded by some negative constant, then you can replace it by corresponding ball in a hyperbolic space. And also, the volume of B is bounded by the volume growth is also bounded. P bar is in the Euclidean space. S is so the growth of the volume is controlled. And this, together with a packing argument, ensures that the second condition is implied by this lower bound of Ricci curvature. So 2 is implied by condition that the Ricci of xi omega I is bounded by minus c for fixed positive constant c. Just for fixed ball, for fixed radius ball in the Euclidean space, we know we can choose such a epsilon net with computable constant of n epsilon. So this Ricci curvature from this definition is quite a Riemannian geometric object. And interestingly, it's very closely related to relation with complex geometry. So on a complex manifold, if the metric is scalar, then omega I is scalar, so the volume form of Gi metric defined by omega I is simply omega I to n factorial. And also, this the same as defines the Hermitian metric on the anti-canonical line bundle. It's HI. So the Ricci curvature, here you see the Ricci curvature is some second derivative of the volume form. And in the complex case, we can define a Ricci form just a relation, like the relation between a Kähler metric and the Kähler form. The Ricci form can be computed using this Hermitian metric. The curvature of this Hermitian metric. And this we know that this is exactly related to the first chain class of Xi. This is one of the most fundamental objects in algebraic geometry. So if we want some condition about Ricci curvature, that's some information on the first chain class of the complex manifold. So we know that for xi we have a limit at x infinity. So our goal is to understand this. Goal is to understand x infinity. Can we extract any algebraic structure on x infinity? So if you look at the examples, we will see that this is not always the case. That x infinity is an algebraic variety. If you just look at curves, so the dimension equals 1. Take a xi, the hyperbolic Riemann surfaces with fixed genus equals g, and curvature equals -1. Then the typical generation is form some long cusp. In terms of this hyperbolic metric. So this is a case where the diameter is not bounded. So if you use that machinery, the Gromov-Hausdorff limits, then if you what do you see depends on where you put the base point. If you put base point here, you will see this part as a limit. because this part diverges to infinity. And then if you put base point on here, then you will see this part. So the limit, somehow the limit should be the whole thing. But each component of x infinity is not does not have a projective algebraic structure. This is one type of phenomenon. It's not what we will focus on later. So also we can take xi to be flat tori, because a torus is a flat metric. Now this is even more complicated. So if you fix the diameter, we can shrink one of the circle. Then the limit will be a circle. Or we can fix the volume, so we expand it. We shrink one circle, but then we expand the other circle. So the limit could be a line, infinite long line. So this space, at least they don't have the obvious algebraic structure. It's one-dimensional Riemannian space. So we impose a further condition so that these two phenomena, at least we want to rule out this phenomenon. So this one, each one of them still is a complex manifold. So for simplicity, let's be more restrictive. Simplicity. We assume. Notice to get this Gromov-Hausdorff limit, we need a Ricci curvature to be bounded below. And let's just assume the Ricci of omega I is lambda omega I, lambda 1. So in particular, the Ricci curvature is uniformly bounded, and these are called Kähler-Einstein metrics. So although we believe the general result should hold, and the more relaxed condition, for example, we just replace this by inequalities. Let's just, for simplicity, just assume they are Kähler-Einstein. And also we assume it's a non-collapsing, volume non-collapsing. So we call this collapsing. This one is not collapsing locally, but at infinity it's somehow getting next, so it's also some collapsing. Let's just assume that the volume of the radius 1 ball around Pi is strictly positive, constant. So this will rule out this situation because the volume goes to 0. Again, we have this assumption we had before. Omega I is 2 pi's. So they are integral. So suppose now we get a Gromov Hausdorff limit by passing the subsequence x infinity. Then we can define a sheaf on x infinity. Of functions. So we know we can choose this metric on the unit of xi and x infinity. So if we fix an open set u in x infinity, we can define x infinity u to be the limit of fi infinity. So we want the shape in the end to coincide with the shape of holomorphic functions. So we just define element in this set to be the limit of functions, holomorphic functions fi on xi. When the space is convergent, there's a natural notion of the convergence of functions. So we want fi to be holomorphic. Because the shape is the limit of the shape of holomorphic functions. This is a pre-shape, and then you can define a shape. This pre-shape. So let me state the result. So all the results state here is joint work with Simon Donaldson. The theorem is that under these conditions, our x infinity or x infinity is naturally a normal complex analytic space. This means that each point has a neighborhood, so that this shape agrees with the shape of holomorphic functions on a complex analytic subvariety of Cn. So any p in x infinity, there is a u, such that u for x infinity is restricted to u is isomorphic to some v or v and Cn is a complex analytic subvariety. And the board is Cn. So the key point is that we get a complex structure on the limit, and the singularities are normal.
So just to clarify, you're not going to get the nodal limits of smooth curves, for instance.
We get each component of the smooth surface of the curve. So in this picture, so I didn't assume the diameter one. I think I need this pi as before. Pi converges to p infinity. So to be more precise, we take p infinity base point. So this one is still complex manifold, smooth complex, in each component though. So when we take the pointed Gromov-Hausdorff limit, we have to choose a fixed. We have to fix base point. So if you fix base point here, then the other component will have a distance infinity. So when you take limit, it will go away. So you only get this part. And if you choose a different base point, you will get different components of this stable limit.
Is the point at the end of the cusp, is that a smooth point or is it a singular point?
We choose smooth point. If we get a single point, then we will get different thing. If we choose a sequence of points converging to a single point, then we might just get the hyperbolic two-side cusp. So if your point lies, actually, so that's a good question. So if we choose base point here, when it's degenerating, right, then this condition will be violated. So the volume around that point will go to 0. So if you don't do anything, then we don't say anything about this.
So your limit could be not compact.
Yes, so as a pointer Gromov-Hausdorff limit. So the X infinity could be compact, non-compact. Because we haven't imposed any diameter condition.
Is there something to be said about the singularities of P or of V?
So at this point, I just say it's normal.
It's not.
So we will impose more conditions later. So this is a remark. Right, so let's go on. Let's just now let's consider more restrictively when the which omega I is lambda omega I. When lambda is only 0, 1, minus 1. So omega I will be either canonical or anti-canonical. So Li will be either canonical mono or anti-canonical line mono, or it's arbitrary line mono, but if lambda equals 0, we fix a parallel homomorphic volume form. Theta I. Theta I bar equals omega I. Yeah. This is the extra condition in the Calabi-Yau case. When lambda equals 0, the manifold is Calabi-Yau. But we want it to be strictly Calabi-Yau, so this which the counting line bond is actually trivial. And we assume the diameter is uniform bounded. So again, our omega I is still in 2 pi. So this ensures the limit is compact. But we have more. So this condition. This was some results we proved earlier in 2012. So here are the extra conditions. Let's just say. So from now on, we will always assume this condition. So then x infinity is a normal projectable variety. and with log terminal singularities. And the xi conversion to x infinity is compatible with flat limits, the Hilbert scheme. This means that we can uniformly embed all the, by classical subsequent, we can uniformly embed all xi and x infinity in some projective space such that the xi conversion x infinity as points in the Hilbert scheme. So this symmetric limit, Gromov-Hausdorff limit, is compatible with algebraic limit in this case.
So in this case, I can see that you somehow compare this sort of metric approach with the Hilbert scheme approach. But in this other case, where you have this non-compact local model, is there a sort of
yeah, so that's the question that I want to ask. So do we have, so somehow the proof, from the proof we will see that somehow locally you can embed a part of x infinity, a neighborhood of xi, so that they converge it to some u in Cn. So we can in an open set in Cn. So they converge like as currents, for example. But so I don't know if there's a notion of a local Hilbert scheme or whatever to parameterize this analytically. Convergence of to describe the convergence of analytic subsets in an open set in Cn. So I can only say that it converges pointwisely or as a current, as a cycle, analytic cycle.
I guess I have a more basic question. So there are moduli spaces of, say, hyperkähler manifolds, which are non-Hausdorff. You can find a degenerated family over the punctured disk that has two non-isomorphic limits. How is that compatible with what you're telling us?
So this is, if we assume the diameter bound, then the limit will be
Well, I mean,
log terminal, and then it will be unique.
they're specializing to smooth projective hyperkähler manifolds.
Smooth projective. That's strange if that happens. If the polarization is fixed, that would be strange.
They're not polarized, is what you're saying? Okay, G says that you can't make them polarized. And so these examples by pointers, they're not polarized. No, but there are higher dimensional cases. Well, I mean, certainly they're projected. So they have manifold windows.
And hold on, is the modular space of smooth polarized non-polarized is just always separated?
Yeah, okay. No, it's even more. So if you assume log terminal, then it will be separated. I think that's Odaka. So we can discuss it later, but I'm sure that there must be some.
So what do you mean by flat limit? Flat limit, what's the meaning of that?
So I mean, there's a Hilbert scheme, and so there's a flat family over this Hilbert scheme, and the convergence is just convergence in the Hilbert scheme. So there's no nilpotence coming up under this limit. So because it's normal. So this is related to Jason's question. So the diameter bound is automatically for if the number equals 1, this is the final Taylor-Einstein manifold. This is because of see that. So before I showed that the Ricci curvature positive controls the volume cannot be big, but also there's this minus theorem that says that if the Ricci curvature is positive, then the diameter, because they have the manifold has the bend, so the diameter cannot be big. So there's uniform diameter bound if the number equals 1. But then, in the Calabi-Yau case, the diameter bound is related to what singularities you get in the limit. So, okay, so Tosati proved that under some mild conditions, I think, the limit has log terminal singularities. If you have a flat family of a puncture disk, and the limit is over the disk, the central fiber is Calabi-Yau with log terminal singularities, then the diameter is bounded for the family of a smooth Calabi-Yau manifolds on general fiber, and vice versa. So I should mention that so the difference from this Riemannian point of view is from the algebraic point of view is that this limit is intrinsic. It's not does not depend on the embedding, and it's unique. You don't get this non-separatedness in this setting.
So that means if you're in this Hilbert scheme, you sort of pick one of the possible limits in the Hilbert scheme by this procedure.
Yes.
So if I take sort of a family and I add all these limits points, what sort of structure does the set have that I get?
I think one is prove that if you have a if you have a flat family over the puncture disk, then the limit should be unique, should be given by this x infinity, and so that the convergence is also algebraic. So you don't need to pass through subsequence.
So just so I understand, you're saying this is canonical, we don't have to make choices, except we have to choose these metrics. I mean, this must be what's going on,
Right, so
hypercable manifolds. If you have moduli spaces, metrics.
so the metric is unique if you fix the cohomology class.
So in the hypercalar case, there's a unique
This is Yau's theorem.
metric. But doesn't you have to fix that extra thing that you told us about? If lambda equals 0, we fix this extra bit of information.
If we fix the omega I in an integral cohomology class, so we choose omega I Li. Then if it's hypercalic, it's Calabi-Yau, then there's unique. Sorry, if we choose this cohomology class, then if the manifold is Calabi-Yau, then there's unique omega I.
But you also got this condition in parentheses. What is this condition?
Well, this just means it's strictly Calabi-Yau. The canonical boundary is trivial. So to get this metric does not mean the canonical boundary is trivial. Yeah, it could be torsion. So I just want to be. That's what I should say. So. under these conditions. So the limit is canonical. So when the manifold is Calabi-Yau, if the number is 0 or -1, this is just unique if you fix this cohomology class. But if the number equals 1 in the final case, because we have automorphisms, non-trivial automorphisms, then if you pull back this omega I by a non-trivial automorphism, then this is still satisfied. So the uniqueness is up to a holomorphic transformation of the final manifold. But as a metric space, they are the same.
Can you say something about which Hilbert scheme? I mean, which is the embedding that you use for this that agrees with this canonical limit?
So there is a k, depending only on the dimension and the diameter bound d, such that our xi, they all embed into the projectivization of n up to passing to a subsequence. So n is the dimension of h0, xi, li to the k. And x infinity also embeds. So the Hilbert polynomial of xi and x infinity are the same.
Is it a particular k or any sufficiently large k?
I mean, there is a k, which this k only depends on n, and the diameter does not even depend on our sequence xi. So this is some universal k. So this is not true for sufficiently large k. This is only true for the multiple of this k0. Because x infinity has singularities. Any other questions? This theory is particularly useful in the final case because the diameter bound is uniform, so the k only depends on the dimension n. But then the condition is that we have to have Taylor-Einstein matrix. The final case is just mentioned that this theorem of Joy, Chen, and Donaldson. That this condition is also algebraic, so final manifold. X admits Taylor-Einstein metric. So if admits, then it is essentially unique. If and only if it is k stable. Right. So this k stability is purely algebraic. I think it's purely algebraic geometric criteria. So I'm not going to talk about k stability in this lecture. So what I'm going to talk about next is about the singularities of this x infinity. So
So is it clear that the limit is of the same type as the things you're degenerating, or close to?
What
Say,
type?
say you degenerate the KXI with ample canonical, do you get at least big on F? What do you get in the limit? I mean,
So
The condition.
if it's carbial, the limit is carbial. If it's funnel, the limit is Q funnel. If it's general type, the limit is a Q general type. So it's so in the limit there is also a line model. The line model is also a portion of proportional to the anti-canonical angle. So there are more information here. Actually, X infinity also means canonic symmetric in some weak sense because of the similarities.
Is the limit before it's done? So it makes sense of it.
Yeah, I think we talked about this before. So log terminal implies.
oh, that's no.
We have to prove it one by one. So we don't prove it directly log terminal. So the log terminal condition is related to the fact that the volume form is the same as the Hermitian metric on the angle. So now if we consider the scaling limit. So now, suppose we have xi converges to x infinity under the above conditions. If we choose a point P in x infinity, so we already make sure x infinity is compact, so the limit does not depend on the choice of base point, so we ignore the base point. Now if you just choose any point, then we can dilate. We can dilate the metric P. Square root of J times distance. So if you have a metric space, a fixed point, you can dilate the space. Because this is already the Gromov-Haskell limit of xi, so this dilation limit, when we do dilation, we can take a diagonal limit. So if you J go to infinity, because xi satisfies the condition when you dilate, the curvature can only become smaller. So we can also take the Gromov-Haskell limit. This is by passing to a subsequence for J. Now this is called a tangent cone at P. Just state this result by Shiger and coding. The tangent cone is always a metric cone. So this is a tangent cone. It's a metric cone. So this tangent cone is just the name. It's just a limit. This Gromov limit. The Shiger coding proves that the limit is actually metric is a cone. So it's a cone over a metric space Y. Y is a compact metric space. So the proof of the previous theorem depends on this theory of the Shiger coding. So using this notion of a metric cone, one can decompose x infinity into the regular part and the singular part. So here, so every tangent cone is isometric to R2n. So this consists of points where when you take this limit, you get the flat Euclidean space, and this is the complement of x infinity reg. And Chiga Coding proved that x infinity reg is actually a smooth Kähler manifold, Kähler Einstein manifold. It's open. So S is a closed set. And the house of the codimension is S should be equal or equal than 2. So here, what we know is that so this decomposition is in terms of a metric space, and this coincides with so the regular singular set of x infinity as a algebraic variety coincide with S. So it's exactly the singular set of the variety that makes a metric singular.
What was the codimension is figuring to 4? So it's normal. Yes. Is it something about the metric that
So in this case, so this later from Chiga Coding can prove that this is actually equal to 4. But in the proof, we don't need this bigger or equal to 4 condition. So if you only assume the lower bound of rich curvature, then you will only get this codimension 2. Yeah. So then a natural question arises. Yes, we can apply the very first theorem I stated that so by the very first theorem, we know that EC tangent cone is a normal complex analytic space because they also satisfy the dilate, they still satisfy the very first condition. And the question is, what is this? At a singular point. If we take a singular point, we get this space. So can we determine this space from the local geometry of the singularity? So in algebra geometry, we also have a notion of a tangent cone, Zariskic tangent cone. But unfortunately, it's in general it's different from the heuristic tangent cone. The heuristic tangent cone can be non-normal. This is always normal. For example, when dimension equals 2, the singularities are all quotient singularities, C2 modulo gamma, gamma in U2. Then the tangent cone will be exactly the C2 modulo gamma. It's flat metric on this orbifold. If you just look at the AK singularities, this is the tangent cone will be non-normal. The heuristic tangent cone. So let me state, the first, we know that this tangent cone is not just a complex analytic, it's always an affine algebraic variety. So the affine structure is given by spec of a ring. So what is this ring? So this ring is a space of all holomorphic functions on Cy. That's holomorphic with at the most polynomial growth. So the polynomial growth is with respect to this metric, Keller-Einstein metric, the limit metric space structure. So we actually proved that this ring is finally generated and it defines the same. So this defines the same complex analytic space as Cy. And moreover, so this is graded because the tangent cone is a metric cone, and the Cheeger coding Kern theory also works for this tangent cone itself. So it's mostly smooth. The singular head are small. So this is a smooth cone, remaining cone. So there's a radial direction RDR, and then if you rotate by J, by the complex structure, you get this is the homomorphic kinematic field. On the regular part of the tangent cone. And this vector field is called Riemann vector field. It generates a holomorphic isometric connection of a compact torus TK. I hope I haven't used a K yet. This K is depends on how this orbit of this vector field behaves. So this is an affine algebraic variety with an action of TK. And this TK action actually gives rise to a positive grading on Cy. That's right. So we can decompose this direct sum alpha into T star H alpha. So these are the weight space decomposition of the TK action on the space of functions. And this is H alpha is non-empty. If I know, implies that alpha psi is positive. So it's a kind of polarized affine variety. So if we take a algebraic projective manifold, we can take it to affine cone. This will have similar type. we get more. It's not just a complex space, it's a outline variety. And we ask what this is. So the first theorem. I state the theorem, but the proof is in different order. So actually, the Cy is unique. This is vague and confusing. So what I mean by unique is it does not depend on the subsequence of J's. So a priori, to check this limit, we need to pass through subsequence. But actually, it does not. So this is unique. So then it makes more sense to ask how to determine this Cy from this local geometry, algebra geometry around the P. So I don't have a definite answer how to do this, but we have some descriptions of this Cy. So if we decompose RCy to be RD Cy. So this is a space of functions f in Cy. Such that the weight of the Kasai action is d. So d is not a necessary integer. D times f. So the weight of the f with respect to psi is a group vector field. And we know that this d is discrete. So this is also this functions f of r x equals r to d fx. If you multiply radially, you get it. So it's kind of the degree of f with respect to the dilation. So S is discrete. Now if we start with any function g in the local, it's a function defined in the neighborhood of P. So this is a proposition. Then we can define vanishing order somehow. So if we have a function, we can define the quantity which is limited as r equals 0 of supremum log over b r and p log f gx over log r. It's somehow like the vanishing order of g at p, but again it's measured by this r is the metric distance to p r x r p distance x p. So this always exists as element in S meaning minus infinity. So, given any homomorphic function, we have a notion of order of vanishing at p, and then we can define a filtration of OP. Equals 0. So ITK is a space of all functions G in OP. So DG equal than DK. The DI is in S. So we can filtrate the local ring and the P by vanishing order, and then we can define a graded ring algebra RP. Okay, IPK over IPK plus 1. So this is a finitely generated. So the spec RP defines a affine algebraic variety WP, affine algebraic. So we hope this is the same as a CY, but unfortunately it's still not yet done. So WP will be also with the TK action. And because of the way we define it, this also has a ripple vector field. So also the same as Kasai. So what does this mean? So we can embed our W and the CY into the same affine space. CY, CN, W, CN. So they will have the same TK action. TK action is a restriction of a linear action on Cn. And they have the same. Some of they're both cones, so they have the same. It's a root vector field Kasai. If Kasai is somehow like 1, 1, 1, the Kasai is rational, then you can take a quotient and you get an orbifold, and they live in the same weight projected space. In general, so this is affine space with a TK action and the positive gradient determined by Kasai. There's multi-gradient Hilbert scheme parameterize these things. And our relation between CY is and W. This is W, CY. So I won't write down the statement. But so there's a C-star action on Cn which commute with Tk, so that the Cy is a flat limit of W under the C-star action. It's a specialization of W. So if you know something about case stability, there's a test configuration. With a general fiber W, central fiber Cy, and it's a TK equivariant.